Okay, hello class. There's one more thing I want to do for chapter 1, which is at the end of your chapter you have these headlines at the top, concept review, calculation review. These are a great way to prepare for quizzes, exams, final exam. I will pull questions from these, and now you get a chance to be prepared ahead of time and see what they look like. So the concept review are going to make sure you understand your vocabulary from the chapter, and that beyond just memorizing, you really do understand a concept. So let me just take an example of one here. At the concept review at the end of chapter 1, here, I'm going to do a couple of these. So number 1 says, true or false, the derivative evaluated at a particular point cannot be negative. So many ways you can think about these is, if you think it's true, it has to be true for every function. And if you think it's false, you just need to come up with one example that shows that is counter to this. One, we call it a counter example. So maybe a way to think about it is visually, what is a derivative? A derivative is the slope of a tangent line. So maybe you draw a function, any old function. And at any point, you can stop and draw a derivative. A derivative is the slope of the tangent line, is the direction of motion. It is, if I zoomed in, the line is going, it would be in this direction. That has a positive slope. But if I drew a point of tangency here and stopped and derailed from the roller coaster, or zoomed in and extended my linelet, this one has a negative slope. The slope is less than 0. So the statement was, true or false, the derivative evaluated at a particular point cannot be negative. So false, because here's a pictorial example. Or maybe you like to think algebraically, and maybe you think about the function y equals x squared. You know it's a parabola opening up from the origin. And maybe you learned that over here, again, some folks might have seen this in pre-calculus, that for f of x equals x squared, the derivative is 2x. Again, you can do that by the limit definition, or in chapter 2, you'll learn how to go from here to here right away. It's one of our easiest rules. Again, if you've seen calculus before, this might be your example because you know the derivative is 2x. The derivative over here at -1, we know it's a negative leaning line, and then you're going to show it algebraically that it's -2. And so you've shown one example, and so you say false for number 1. Okay, let's just do one more concept review. It's another true false. Is it possible, it says for a function y equals f of x, or y equals f of x, it is possible for f prime of a to equal f prime of b when a is not equal to b. Okay, that seems kind of messy because, like, hey, what are we talking about? There's all these symbols and letters. And my advice is, again, to try to think visually for a lot of these and see if you can come up with examples or counterexamples. Don't be frightened by these letters. Just say, oh, when a is not equal to b and these are a and b are x values, right? We're plugging into the derivative. You're saying, hey, is there, like, maybe put in your favorite numbers, like when a is 1, it's saying f prime of 1 equals, and put in another number like 3, maybe. So I guess my point is, this is written generally, but you could make it specific and see what you can figure out about the problem. Once you've made it specific, then make, instead of 1 and 3, try 1 and 4, 1 and 5, or just try a couple other and see if your intuition holds. Your answer would continue. So when it's general, don't be frightened by the generality. Make it specific temporarily and go from there. Okay, so it's really saying, for a function, is it possible at 2 different x values to have the same derivative? All right, well, what does derivative mean? We've got this notation, f prime. The derivative is a function, but it also means a slope of a tangent line, or an instantaneous rate of change. I think the one that's most helpful here is the slope of the tangent line. It's saying when x is 1, the slope of the tangent line at 1 is the same as the slope of the tangent line at 3. Is that ever possible? Let's try to draw a picture. So at 1 and at 3, we're at some point on the function, and we have the same slope. So what's a function that could do that? Well, there's infinitely many, but I'll just draw one. Maybe there's one that went like this, Oops. Right? But here's an even easier one. Hopefully you saw this right away. At 1 and at 3, I don't care where we are, but as long as we have the same slope. A straight line would do it. A straight line like this. At 1 and 3, you have the same slope. So is it possible for a function for any a and b, as long as they're not equal, that it's possible they have the same slope? Yeah, we've shown several examples here. All right, so those are a couple examples of concept review, and it's a good thing to go over, again, work through those. The answers are there for those. And then the calculation review, I want to work a couple of these. It says, let's look at number 1, 1a. It says, use a TEK tool to graph each function and estimate the instantaneous rate of change at the indicated point. And so I'm sure you have your favorite TEK tools. You can use any calculators this semester that maybe you've got one you're familiar with, but there's also a lot of free resources online. And so that makes it particularly suited for this learning environment. So I'm going to share the screen and just show you a few that are available. All right, so I'm just going to go to Google and type in y equals x squared. And, whoops. Maybe it's set to graph it. Nope. Let's see. Try. Okay, there. For some reason, the y equals x squared had too much other information I was looking for, but usually enter any function and it'll show. What's a little bit different is that the scale is odd, so you can zoom in and zoom out here. It shows you as you're tracing along the curve in this corner here, the x and y values. But notice again that the x scale is like 2, 4, 6, 8, but the y scale is much bigger, which it automatically scales that. And so you may need to learn how to zoom in and out. But another easy tool to use is something called Wolfram Alpha. Or just type in Wolfram, you'll probably get there. And this is a natural language processing thing. So you can say graph y equals x squared. Whoops. Need a space there. And so it's prepared to take as input what you can write in English language and plot the function which it shows here. And another one you're probably familiar with is Desmos. So we'll go to that one next. Let me stop the screen share for a moment and just pause. Okay, so again, we want to check out one more TEK tool that you can graph. That's available for free on the internet. And Desmos, graphing calculator. And you can just enter your function here, y equals x squared. And there's our parabola, again, our familiar friendly parabola. And then over here in the corner, there's some ways to zoom in and zoom out, change some of the settings, the axis, x and y axis, like you would make a little frame as you would in your calculator, your TI calculator. Okay, but I also want to show you another TEK tool. So we can say Desmos tangent line calculator, because we're doing a lot of stuff with tangent lines this semester. I think this first one will do it. Okay, so this has a function already set up for us. And it's gonna, this is sine x plus 0.3x. We don't do a whole lot this semester with trig stuff. So maybe let's go ahead and just put some sort of parabola or some other function in. Let's say x cubed. Let's try x squared, an exponential e raised to the minus x. Let's see. Okay, so that's an interesting enough one. We can scroll over. And what it has is little slider. This is your x value. And as you change your x value, it's showing the red line is your tangent line. So at any point on the curve, the tangent line exists, and it could be You'll have a different slope depending on which point you're at. And then the other point is showing that little red one that's dragging around here is showing, it's an estimate, or it's a visual indicator of the slope of that red line. So that is a negative, a small negative value. And you can see that the line is negative leaning, but small. And then it's going right here to exactly 0, which, what's our vocabulary for that? That's a critical point when you have a horizontal tangent line. And then you move a little bit here. When x is about 1.5, you can see that you have a positive leaning line. The red line is leaning in the right direction. And you can see that the red dot is a positive value, right? It's a y of like 0.2 or something, right? Positive, 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 increasing positive, a little less positive, and then back to 0 again. Another critical point here at x equals 0. And it looks like another critical point right here at x equals 2. And so this is a fun one to visualize the tangent line. You can enter any function you want and slide it along. Watch that derivative change. Okay, stop the screen share. And now we'll work a few problems then. You can use these tech tools. I want you to check and visualize your work. I want you to use the tech tools this semester, but you still have to understand the concepts. Okay, so number 1 said use a tech tool to graph a function y equals x squared, estimate the instantaneous rate of change at the indicated point. So I just showed you how you can do that with Desmos. But you could also do it by hand. Just graph y equals x squared with Wolfram Alpha, go to 2, and estimate the slope there. If your graph is to scale, it's pretty easy to estimate, but you can always say whether it's negative, 0, or positive. Okay, and number 3 says find an average rate of change. And like, for instance, here's the problem. 3a, find the average rate of change of y equals x squared at from x equals 2, sorry, from x equals minus 4 to x equals 2. Okay, so you can do this just cranking away with the algebra, or you can think of the picture. So y equals x squared, you can use a tech tool if you don't remember that it looks like this. And we're going to go from 2 to minus 4. So it would be something like this. Connecting dots makes it a secant line, and we want to get the slope of that secant line. So the slope of this line is change in y over change in x. So I just need to figure out what are the coordinates of these points. When x is minus 4, what is y? Again, always go back to the original function when you want a y value. So when x is minus 4, you square that and get the y as 16. Over here at the point 2, y would be 2 squared is 4. Okay, so then I just subtract the y 16 minus 4 divided by, subtract the x's and make sure you do it in the same order. So minus 4 minus 2 is 12 divided by minus 6 is minus 2. So then just check yourself. Is it a negative leaning line? Yes, we got that part right. And they didn't give us units for this, so we can just say it's a slope of minus 2. The average rate of change is minus 2. Had this been a word problem, like y is the number of Facebook users, x is time, your answer would be it's decreasing. You're having -2 Facebook users per year, if that were units. Okay, let's do number 4. I'll do 4a. Quickly run through these. It's saying this time they want you to get the equation of the tangent line. So now we get to put together stuff from the module 0 preview about equations of lines. Find the equation of the tangent line for f of x equals x squared with derivative. They're giving you the derivative. They didn't ask you to find it, which is nice because you didn't have to use the limit definition. The derivative of x squared is 2x, and you want the equation of the tangent line at x equals 2, at the point x equals 2. All right, so let's draw a picture. I'm going to tell you to do that. That's going to be my advice repeatedly throughout this class. Draw a picture to visualize what's happening. The function, again, you remember what it looks like, or you just get out a tech tool or a calculator and graph it. Maybe use Desmos, got to there. Maybe use the Desmos with the slider and said when x equals -2, you slid that tangent line right up to here, and it would have estimated or shown the tangent line here. So we always usually do those in red, so let me go back and put that in red. So this is the tangent line. We know that the slope of this tangent line is, in notation, f prime of 2, right? We know that because that's by definition. Right, so we want to get, we know the slope of the tangent line is just plugging 2 into the derivative function, which is easily 2 times 2 is 4, no problem. So this line has a slope of 4. But the question said, don't just get the slope, it said get the equation of the line. So now we have to piece together some stuff from the preview work. We have the slope of a line and we have a point. Okay, so what is the point that we're at? This is the point when x is 2, what is y? 4. So another way, at this point, another way of answering this question is saying, find the equation of the line going through the point 2, 4 with a slope of 4. Right, and that we can do. We know lines, like tangent lines are lines like any other line, and they always have to be in y equals mx plus b form. We already know what the m is, that's 4. We just have to figure out what the b is, and we'll be done. Well, how do we do that? There's like 3 letters right now, but we know 2 of those letters. We know x is 2 and y is 4, right? Because points are always x, y. So we can plug those in. So we'll have 4 times 2 plus b is equal to 4. This is one equation, one unknown. We can solve for b, and we'll see that b is what? -4, right? B equals -4. So then our equation, y equals mx plus b, equation of a line, and for us it's the equation of the tangent line, is y equals 4x minus 4. Does that make sense from our picture? Let's come back to the picture. Does the slope, is it a positive leaning slope? Yes. Is it going to go through a negative y-intercept? Yes. Another way you could check your work is to go to your tech tool. So go back to Desmos and graph both the original function and the tangent line and make sure they touch. They should barely touch, because remember the word tangent means touching or kissing, caressing. This tangent line just caresses the function just barely at x equals 2. If it does anything else, like if you graphed, you got some answer, you graphed the original function, you went to x equals 2, and it did something like that, you know you probably did something wrong when you did your work here to get the tangent line, right? It has to look, the picture has to look like that. So let's just quickly check with the tech tool, share the screen, pick your favorite grapher tool. Let's go back to the Desmos one. Oops, this one. Oh, that's not the Desmos. Let's go back to this Desmos graphing calculator. We'll put in the original function was y equals x squared. Okay. And then we'll put in the tangent line, which is y equals 4x minus 4. There's our tangent line. And then does it just barely, let's move this down a little bit, barely touch at 2? Yes, it does. That is exactly what we're looking for to make sure we've checked that we've done our work right. Yep. At x equals 2, 4, which is again with our point of tangency 2, 4, it just barely touches. Okay, so then let's do, again, number 5 in your calculation review is asking you to use the limit definition. I'm not going to have you do those, so you can skip ahead. But as opposed to number 4, where I can ask you things about the derivative and I've given you the derivative. Right? Okay, so we'll skip ahead. 6, again, using the limit definition. I'm not going to make you crank away on those. Okay, let's do 7. Let's do 7D, let's say. says determine if the function, and the function we're looking at in D is function f of x is increasing, decreasing, or neither at the point x equals minus 5, where the derivative f prime of x is given. So someone did some work and figured out for a function f, which again, they're not even giving us that explicitly or algebraically, but they are giving us a function for the derivative. And they're saying, at that point, x equals 5 on this function, we don't even know what it looks like. Maybe it's like that. It's saying at x equals minus 5, maybe that's here, is the function increasing, decreasing, or neither? And we have the derivative. So remember the connection between the derivative, increasing, decreasing. If the derivative is positive, that means the slope of the tangent line is positive. That means you're pedaling uphill. Your function is increasing. So all we have to do to answer this question is to plug -5 into the derivative and see if we get a negative number or a positive number. So f prime of -5 is going to be negative of -5 plus 3 squared, which is a negative -2 squared, which is a -4, which is less than 0. So that means at x equals -5, your function is decreasing there. So this wasn't the right picture. Clearly wasn't the right function. What we do know, we don't know what the original function is, but we do know over here at -5, at some point wherever you are, maybe that's the point on the function, you have to have a negative, a pretty steep negative, right? -4, pretty steep negative line. Actually, that's a positive line, sorry. Negative line. Right, it has to be pretty steep negative, which means you're decreasing, you're going downhill. Okay. Yeah, I think that's all I want to work on this. So you can practice these. Again, answers are, there's a whole other page with answers. Check your work. This is a great way to be prepared for quizzes and exams. It's also a good thing to go through these and then bring me questions, office hours, bring questions to the math lab, bring questions to any virtual classes we will have. Right, enjoy, have fun.